Hello, everyone. Uh, Welcome. I'm very excited to show you something I've been working on for quite a while, and that I was recently able to really get out there using GPT 5.6 Sol. This is a modeling environment called LibeR. LibeR is Latin for book or free, and the LibeR environment enables us to run pharmacological models for various purposes. The core of this environment is built around a package called LibeRTat, which is an automatic differentiation engine using C++, but the code you can write yourself can be written in R, but then in the background it uses C++ to automatically differentiate your models. Now, the first package I wanted to show you here is Liberation. Liberation is really a user interface built for model building and model execution. So let's start a new project here. Let's call it test, and let's create this from a template. There's an example here, Theophylline, just a standard demo. We create the project, and there it is. We have a model here, and it's just a standard one compartment model. I won't go into too much of technical details, but it has already the template code in here. And let's run this model. We could do it on a remote server, but we'll use the local queue for now. I want the covariance step so I can get the uncertainty around the parameters, and we run the estimation. We see it show up as running there, and that's it. It's very fast, very efficient. Now, when I click on this, I can get goodness of fit plots here. This is something the environment does automatically. It takes a second to generate, and there are the plots. These are some typical plots that most people will want to see when they want to assess the goodness of fit of their model. I can run some extra diagnostics, for example, a VPC or a visual predictive check. Um, let's run that real quick. Takes a couple seconds to run. And there it is, a badge appears, so it shows that the VPC was made. And there's the VPC. And similarly for the other diagnostics, you just run them here and they automatically show up in your workflow. So it's very intuitive, it's very easy to find things. And you can find the parameter estimates here on the right hand side with the covariance matrix. There's even some information about how long it took to run the model. It was very short, as you can see here, less than a second. There's even an AI help. I've turned it off for this demo. It's still a work in progress, but it is working to a certain degree. The main limitations, of course, being the person's hardware, because this all runs in your personal browser. It might be difficult to make the whole AI run on your local hardware to a sufficient degree where it is able to say something meaningful about your models. You can see also here a model log. You can clear these, you can cancel ones that are running. Well, these are not running, so canceling them won't do anything. You can add new servers. I have one server added here that is running in the background, and I'll show you now. That is called Liberties. Liberties is a server. It comes with its own server admin panel. As you can see here, you can add users. This is me. You can set limits on each user individually. You can rotate tokens, which are used to log into the server to send it jobs. Has its own job queue here. You can see I ran an estimation earlier. You can cancel jobs. You can see some overall stats for the server. So it's very useful. As you can see, every user interface has a light and dark theme. Every user interface also is themed according to what it is. So blue for liberation, red for liberties. And then we go to liberality. Liberality is a program that allows you to do study design optimality. So that enables you to employ these same kind of models to run estimations that help you to determine how to set up a clinical study as efficient as possible. So when we look here, we can see all sorts of constraints. There needs to be at least 30 minutes between blood samples. We need to have at least, or at most, 90 subjects, etc. You can set all these parameters. You can make alterations, change the arms. So there's two arms in this study. A small number of people will have a dense sampling schedule, and a larger proportion of people will have a sparse sampling. So there will be less samples for those. Now, if I want to know how well will this design do, I click on Evaluate Design, and the results are in within moments. So we go to Precision. In Precision, we can see how well we are able to estimate the parameters that are in the model. We can see how robust the study would be, and we can optimize. So we can say there's various algorithms. Please design this study in a way that I know will result in the best information to be gotten from the sampling, from all the design characteristics. So you see the log determinant, which is a number that has a correlation with how efficient the design is. It has gone down a bit, so it's improved. And you see here the optimization convergence. So this is how the model basically finds a solution, the optimal solution. It gives you here an overview of the optimizable variables and what the outcome was. And then we can also run a simulation. So based on the study design that was just determined, let's simulate. Let's do 20 clinical trials, and we refit and run those simulations to determine how well in reality that study design would work out, considering that there's going to be variability across the study design, study execution as well. Every time you run a study, you don't get the same type of people. There might be differences, and so in this case, 80% of the times out of those 20 trials, the model will converge and find acceptable results. So that's in a nutshell is liberality. There's a lot more to it, but I'll go to the next one due to time constraints. The last one I wanted to show is LibeR. LibeR is a clinical decision tool. It helps you to determine what the individual characteristics are of your patient and then adjust the dose or other aspects of the treatment to the patient. In this case, this is an example from anti-epileptic drug therapy. We assume for a moment that we want the drug concentrations to stay between 2 and 8 milligrams per liter. We already have some data in the system. This is my test patient. We have some concentrations. The concentrations have changed. We have some other data here. The dose was given, was entered here as information, and then later it was confirmed still on the same dose, 300 milligrams. Weight was initially weighed here at 68 kilograms, and then later at follow-up it was missed. That's okay. And we have these concentrations that were measured. So you see that here on the timeline, and you see these arrows that indicate sort of what we call a state. So between these arrows, that's one state of the patient, and then from that next arrow onwards, that's another state. And we can add states here, and we can add covariates, for example, weight, age. We can add TDM, therapeutic drug monitoring. Those are the concentrations. We can change the dose at certain times. So let's add another concentration measurement. Let's say that's at 180 hours. And let's say we measured 8 milligrams per liter. We add it to the timeline. There it is. And now I want to update what the clearance of the drug is. So I want to understand how fast is this patient clearing the drug. And here we have the variables that determine this. So you see that on 2 occasions in 2 states, they have different values that correlate to how much the patient deviates from the typical patient. And now we can explore candidate regimens. So regimens that will attain the concentrations that we're looking for. You can give the dose amounts. Let's say there's 100, 200, and 300 milligram tablets. You can give, or 100 and 200, and then you can combine that to 300. Let's say you can give it either every 12 or 24 hours, and I want to evaluate up to 180 hours for now. And how many people do we want to simulate based on the estimations we just did? It runs the simulation, takes a couple seconds, and there it is, and it gives me target attainment. So how well do we stay within those concentrations? And this is almost 100% if we give 200 milligrams every 12 hours. Well, that's interesting. Let's see what that means in reality. We generate a future prediction. And we see the concentrations over time. Of course, every 12 hours, concentrations go up and down because you give it every 12 hours. And you see that indeed the shaded area, the concentrations by and large stay within those measures. So that really helps the clinician to make decisions. It shouldn't be taken as an oracle. This is not something that tells the clinician what to do, but it gives the clinician additional information that he or she can work with to better treat their patients. And I think in total, these uh, packages are useful in various ways, but the core concept remains the same. They use these pharmacometric models. Now, one more package that I cannot show you right now, but is also available, is LibeR. And this, as you may already understand from the name, it's a model repository. And what it does actually is it goes through PubMed and finds articles that may or may not contain pharmacometric models. Then it has two parallel paths, a VLM and an LLM, that will extract information from that same article. The results of those two paths are compared against each other, and if there's differences, a third, more advanced model will educate which of the elements is the best. And this will be compiled into a repository, and then it can be human reviewed as well, and the human can make changes or decide whether things have to be changed. But once a model has been reviewed and approved, it ends up in the repository as uh, accepted, and these can then be fed into each of these uh, packages. So here in Liberation, if we go back to the home, you can see here the model library. It's not connected right now, so I can't do that right now. But you can create a new project. You can start from a model that's from literature and start running some simulations, and it will speed up tremendously your workflow, because that is something we really don't have right now in our environments. So I hope you found this interesting and useful, and thank you very much.